Hi everyone, welcome to the third video in the Haskell series. Today I'm going to be talking about syntax in functions, and I'm just going to be exploring some of the syntactical constructs that are present in Haskell. So the first thing I'm going to be talking about is pattern matching. So what pattern matching is it consists of specifying patterns to which some data should conform to, and then checking to see if it actually does and deconstructing the data according to these patterns. So when defining functions, you can define separate function bodies for different patterns. This leads to really neat code that's simple and readable. You can pattern match on any data types such as numbers, integers, characters, lists, tuples, and many more. So let's make a really trivial function that checks if the number we supplied to the function is the number 7 or not. So we can quickly define a function called lucky. So as you can see, when I pass the number 7 into lucky, it gives the output lucky number 7. So we can see that obviously, well, the number is lucky. So the patterns will be checked from top to bottom, which is a key component of pattern matching. It's not checked from bottom to top. It goes in order, checking from top to bottom. And the only way a number can conform to the first number in this particular example is if it's 7. So since in this example, the number is 7, it obviously prints out lucky number 7. And if it's not, then it falls through to the second pattern, which is the third line, lucky x is equal to sorry, you're out of luck, pal. And this function could have also been implemented by using an if statement. So pattern matching is quite similar to if-else statements in other programming languages, such as Python. But what if we wanted a function that says the numbers from 1 to 5 and says not between 1 and 5 for any other number? Without pattern matching, we'd have to make a pretty convoluted if-then-else tree. But pattern matching allows us to make it just a lot easier. So this is an example of some code that does this. So I've defined a function called sayMe. It takes a string, which is quite important. So we need to pass it takes a number, but it outputs a string. So if I call sayMe and I call the number 1, as you can see, it outputs the string 1 exclamation mark. And if I say sayMe 2, then it passes the first pattern, goes to the second one. But if I say me 6, which isn't in any of the options, it goes to the last one and it prints out not between 1 and 5. So this is kind of a catch all numbers pattern, and it's normally used at the end of pattern matching code. So we can do a very similar thing with recursive functions as well. So we can make recursive functions using pattern matching. So far we haven't actually used recursion, but it's very important to be able to do that in Haskell. It's a very key component, recursion. So an example for using recursion as a function would be in obviously the factorial function. The factorial uses recursion. So this is an example of some code that makes use of recursion, as well as pattern matching. So factorial takes in an integer and outputs an integer. So if I pass factorial 3, for example, it outputs 6. So basically what happens is every time it loops through the code. So for example, in this case, we've done 3. So what it does is it isn't factorial 0 because the number isn't 0. So it goes to the second pattern. It goes to factorial n is n times factorial n minus 1. So what it does is it computes 3 times factorial 2, and the factorial 2 is broken down to 2 times factorial 1. And then basically at the end, we have 3 times 2 times 1 times factorial 0. And then it reaches pattern 1 on the last run through the code. And it sees that factorial 0 is actually 1. So it's kind of breaking the loop of the code and the loop of the recursion. So it says factorial 0 is 1. So it just substitutes 1 in for that. So it's just 3 times 2 times 1 times 1. which we see as an output of 6. So yeah, so recursion is quite effective and quite simple, as you can see with this code. But there are also instances where pattern matching can fail, and these are instances that we should avoid with our code. So this is some code that would lead to pattern matching failing in Haskell. So I've defined a variable called character name. So it takes in a character and outputs a string. So I can pass in A, and as you can see, it works. It outputs Albert. If I input B, it outputs Broseph. But if I input a letter like N or L, as you can see, an error is being thrown because we haven't taken into account for that specific condition. So it complains that we have a non-exhaustive pattern, and this is rightfully so. When making patterns, we should always include a catch-all pattern, as we did in the previous code, so that our program doesn't crash and we don't get an unexpected input. Pattern matching, as we've discussed before, can also be used on tuples, not only characters and integers. So we can add vectors in this example code. So if I run this, add vectors, yeah. So what the code does is it takes the first element of the first tuple and then adds it to the first element of the second tuple. So in this case, it's adding 2 and 2. And then it forms another tuple as that being the first element in the tuple. And then it adds the second integers of the two tuples. So this is an easy way of using pattern matching for adding two vectors. And there's actually a better way to do it. So we can modify the function using actually using pattern matching. Sorry, this doesn't use pattern matching, obviously. So this code does use pattern matching, and it should output the same thing if I pass the same tuples. Yeah, so it gives the same output. So as you can see, we use FST and S and D. I think we did cover this in a previous video. That is pretty much first and second. Cool. Now we can go on to head functions. So an example of some code for this is here. So we can actually give an empty list. Can't call. Yeah, so it gives the exception can't call head on an empty list dummy as we wanted it to. So we actually printed the error, or we gave out an error manually using the code. So yeah. So basically the notation x:xs pattern is used quite a lot in Haskell, especially with recursive functions. So you can see that I used x:_, in this example. So patterns that have a colon in them only match against lists of length 1 or more. Yeah, so if we use a head function with an example like 4, 5, 6, then it prints out the head that is 4 of the list. And since we haven't defined a specific variable, a specific type for the input, we can even put a string. So head We can put any string like hello. So it should print out oh, there should not be a brackets or a square brackets around because it was not specified. Yeah, so it prints out capital H as a head. So now we can make a trivial function that tells us some of the first elements of the list in convenient English form. So we can make the tell function that does this. Also, it's really important to notice in your functions what inputs and outputs you're taking in so that you don't run errors. So for example, here, yeah, so it goes into the first pattern when we say tell with an empty list. So it prints out the list is empty. And we can do tell, oh, you could pass a string. The list has one element, and then it shows us the element. We could put more than one. Yeah, the list has two elements, hello and my. And we could say, oh, list is long, the first two elements are hello and my. So as you can see, the code works just fine. And the function is safe because it takes care of the empty list, a singleton list, a list with two elements, and a list with more than two elements. So the catch-all code at line at the end, which we've been talking about extensively. And you can note that the line over here, x colon square brackets, could also be written as just x in this way. And the same thing goes for x colon y colon semicolon square brackets. So this could just be written as x comma y, and the code would still work. Yeah, so we've already implemented our own length function as well using list comprehension, and we can do the same thing with pattern matching as well. So this is just an example of how to do that. So yeah, so we can do length. Hello. Oh yeah, so I guess that needs to show. Yeah, so as you can see, it works. So in this case, we had one element in the square brackets, that's hello. Here we have two. And yeah, clearly, this is similar to the factorial function that we wrote earlier. First, we define the result of a known input, which is the empty list. And then in the second pattern, we take the list apart by splitting it into a head and a tail. And we say that the length is equal to 1 plus the length of the tail. And we use the underscored to match the head because we don't actually care what it is. Also note that we've taken care of all possible patterns of a list with the code. The first pattern matches an empty list. And as I was just saying, the second one matches anything that isn't an empty list. Cool. So we can do the same thing with sum. I'm just giving a lot of examples here. So this is the last one for pattern matching. So the same thing works for sum. This is just for you to get a feel of how pattern matching works and just how effective it is. So you can have sum of 1 and 2. So you can see it's 3. Sum of, let's say 8 and 32, 40. So yeah, it's just basically what we've been talking about this whole time. Yeah, so we can use sum for pattern matching as well. So whereas patterns are a way of making sure a value conforms to some form and deconstructing it, so that's basically what pattern matching does. Guards are a way of testing whether some property of a value is true or false. So it's again quite similar to an if and else statement, and it is. But the thing with guards is that they're a lot more readable to the eye when you have several conditions, and they are quite nice in tandem with patterns as well. So we can go straight into the code for guards, and guards pretty much work on Booleans, true and false, basically. So this is just an example code for BMI. So if my BMI was, say, 25, yeah, so it gives the output, you're supposedly normal, I bet you're ugly. So guards are indicated by pipes that follow a function's name and its parameters. Usually they're identified a bit to the right and lined up, as you can see in the code over here. There's an indentation as well. So you need to follow the syntax extremely well, otherwise it won't work. So as I was explaining before, a guard is basically a Boolean expression. If it evaluates to true, then the corresponding function body is going to be run. And if it evaluates to false, checking drops through to the next guard, and so on. So it's, again, very similar to patterns, very similar to if and else statements. Yeah, so there's another part of guards called otherwise, which is kind of the catch-all function that we were talking about. So you can see that in the bottom. Otherwise, you're a whale. Congratulations. Yeah, so otherwise is simply defined simply as otherwise equals true. So that's kind of the else statement if in an if else statement in any other language. Yeah, so we can actually the difference between so we can actually use guards with functions that take as many parameters as we want. Instead of having the user calculate his own BMI before calling the function, we can modify this function so that it takes a height and weight, and we can calculate it for the person. So this is easily done with a small addition to the code. So as you can see, we've done weight underscore height squared, and we take the weight and height as parameters of the function. So we can load this up. BMI tells, so I can give my own statistics. My weight is 60 kgs, height 1.73. So it calculates my BMI for me, and it says you're supposedly normal. Yeah, and also note that there's no equal to sign right after the function name and its parameters before the first guard. So that's very important to note. And another example, instead of a BMI calculator or BMI calculator, you can use the max function, which we've been talking about previously as well, with guards. And yeah, so we can do this. We can run this code. So if I want the maximum between 8 and 9, so it goes into the guard function. It goes to the first one, a greater than b. In this case, a is 8, b is 9. So this statement is false. So it goes to the otherwise function, and it prints out b, which is 9. So we can see 9 is a bigger number between 8 and 9. And yeah, that's the maximum. That's the larger number. Guards can also be written inline, but it's preferred not to be done in that way just because it looks quite messy. So I'm just not going to bother to even show you how to do that, because don't. Yeah. So there's also a where function inside, or not inside, but part of the guard functionalism. So going back to the BMI function we made earlier, we can add a where. Yeah, so we can run this again. BMI tell, again, I can put my stuff. Oh. Yeah, so it says I'm normal. So essentially here we put the keyword where after the guards. Usually it's best to indent it as much as the pipes are indented. So you can see here it's indented the same amount. And then we define several names or functions. So these names are visible across the guards and give us the advantage of not having to repeat ourselves. If we decide that we want to calculate BMI a bit differently, we only have to change it once. So it improves readability by giving names to things and can make our programs much faster since like the BMI variable here is calculated only once. So we could even present our function like this using the where function. So I can give the same things I have been, and it gives the same output. You're supposedly normal. I bet you're ugly. So here on top of calculating my BMI, it gives a value for skinny, normal, and fat. And then it goes to the guard statements and evaluates the Boolean expressions and outputs the values. Yeah. Cool. So we can make another trivial function where we get a first and a last name and give someone back their initials using where. Uh, so again, remember here we're working with strings. So I need to give in a string, first name and last name. So mine is Aman Berman. Yeah, A dot B dot. So yeah, that's again using the where function. So we have so we've given we've kind of tied f colon underscore to first name, which we input as or which we put as one of the inputs, and yeah, so this is the where in action again. And so just like we've defined constants in where blocks, you can also define functions. So we can make a function that takes a list of weight height pairs and returns a list of BMIs. Yeah, so you can do the same BMI thing. And we can give it a list. I mean, we don't need to go through this. It would take quite a bit of time. So there's also a let it be function. So this is very similar to where bindings are let bindings. Where bindings are a syntactic construct that let you bind variables at the end of a function and the whole function can see them, including all the guards. Let bindings let you bind to variables anywhere and are expressions themselves, but are very local, so they don't span across guards. Just like any construct in Haskell that is used to bind values to names, let bindings can be used for pattern matching. So yeah, let's see them in action. So we can do this specifically to find the surface area for a cylinder, for example. So we can show the let it be syntax. So I can just give in any radius or height, and it outputs the surface area. So as you can see, the form is let bindings in expression. So you can see that these are the bindings in this expression. So the names that you define in the let part are accessible to the expression after the in part. And as you can see, we could also have defined this whole thing with a where binding. So it's very similar to what we were just talking about for the where binding. And notice that the names are also aligned in a single column. So the main difference between let bindings are that they are expressions themselves, whereas where bindings are just syntactic constructs. So remember when we did the if statement and it was explained that an if else statement is an expression, so you can cram it almost everywhere. We can also do that with a let binding. So I can copy this straight here. So if we just look at this closer, if 5 is greater than 3, then woo less else boo. If A is greater than B, then foo else bar. So obviously 5 is greater than 3 and A is not greater than B. So it prints out woo and bar because we have else bar in the second expression. The second one, 4 times if 10. So obviously 10 is greater than 5. So we take 10 as the output. So 4 times 10 plus 2 is 42. So it's quite simple. It's very similar to the previous embeddings. Yeah. So just finally, case expressions. So many imperative languages have case syntax, and if you've ever programmed in them, you probably know what it's about. It's about taking a variable and then executing blocks of code for specific values of that variable, and then maybe including a catch-all block of code in case the variable has some value for which we didn't set up a case. So Haskell takes that concept and one-ups it. Like the name implies, case expressions are expressions, much like if-else expressions at let bindings. Not only can we evaluate expressions based on the possible cases of the values of a variable, we can also do pattern matching. We can just quickly show the syntax. So this is the syntax of case expression, and it's really simple. So you can see it as that case expression of pattern gives result. So again, it's quite similar to the other syntax that we've been looking at, such as let and where, in particularly quite similar to where. So yeah, so I can give some example code. So this is what this describe list function looks like with case expressions. And this is what it looks like in where. So you can see how similar it is. This is the code that we did at the beginning of the video. So it's very similar. In fact, I can run the first code and show that they also produce the same output. So describe list. Again, notice that it's a string needs to be passed. Oh. Hmm. Yeah, for some reason it wasn't working there, but rerun the code. And as you can see, this list is a singleton list. And if I add more elements, it should output, this is a long list. So yeah, that's it for case expressions. You can see the syntax. And just one last thing, this translation for the where embedding is very similar, as you can see. And yeah, so we should be able to get the same output if we run this as well. Hopefully it works. It doesn't throw there. So I can literally the same stuff. Yeah, singleton list. Cool. So as you can see, same outputs. Yeah. So that's it for syntax and functions. Next week, we're going to be talking about recursion. So I hope you enjoyed the video and see you next week.